Hello everyone, this is Mr. Taylor with Young Engineers Today. This is our first webinar of Ancient Engineering. We'll be focusing on ancient technology this week. This is an introductory video about mankind and engineering. It's about 3 minutes and some change from the History Channel, kind of get us amped and introduce us into engineering throughout the ages. You can find this link on Edmodo for this video. Here's a quick video at this mechanism that was discovered around the early 1900s in the Mediterranean. It is an ancient Greek tool that was used to look at lunar calendars, predict when Venus would be moving. Very, very advanced ancient computer, if you will. Here are some video links for you. They're already been posted on Edmodo. The first one is about 7 minutes long. The other is a full hour, so you can dig in deeper. All right, as I said, shipwreck over 100 years ago. It's named after the island. The ship sank during the times of the ancient Greeks. They discovered a blob of rock was found among the debris. Using X-ray technology, scientists have discovered it was a mechanical device. It was a calendar, a celestial guide. It listed the Olympic events that were scheduled every 4 years, but it was made up of simple machines. Now, let's go over some terminology first before we continue. Definitions. Force. Force is a push or a pull, as an example in these images. Work. Work equals force times distance. All right. Now, with work, when force and displacement are in the same direction, work equals force times distance. Okay. But what's important here is that the direction of the force and the direction of the object moving are the same. Okay. For example, here you have this weightlifter. He has his force. With work, he lifts 25 kilograms, 2 meters. Okay? So you have a force and a distance. Now, sometimes things look like they're work and not work, because what's important here is the direction of the force and the direction of the motion. As you can see in this image, you have to have a clear direction of force and direction of motion to be measured. Now, we use the word work a lot, but it has a different meaning when you're using it with regards to science versus outside of the science realm. Scientific definition of work is using a force to move an object a distance when both the force and the motion of the object are in the same direction. If that's not clear, you can't determine work. All right, so don't confuse effort with work. Pulling on a locked door is lots of effort, but there's no work because the door did not move any distance. Okay. All right. Now, here's 2 examples. A teacher lecturing to her class, a mouse pushing a piece of cheese with its nose across the floor. Obviously, the mouse, because you have a direction and you have a force, are the same distance. All right. Now, the mouse is using a force to move the cheese a distance, but the force and motion are in the same direction. Now, here's a few to look at, all right? And the thing you got to remember is that force and direction, okay? Now, some just terminologies. We use newtons is the unit of measurement for force. The unit of distance is meters. The unit of work is Newton meters. 1 Newton meter is equal to 1 joule. The unit of work is called a joule. Okay. Now, here's an example. It's a practice equation. If a man pushes a concrete block 10 meters with a force of 20 newtons, how much work has he done? He's done 200 joules, which is 20 newtons times 10 meters. Okay. There's more practice problems. Those have been posted on Edmodo. A link for those. Now, ancient engineering, what is power? Power is the rate at which work is done. Power equals work divided by time. But we remember this becomes a complex equation because work is a made-up equation of force times distance. And we measure power in the unit of watts. Okay? Now, there are some practice problems, and this helps you do the equation as well as the inverses. So sometimes you would have to find the work or find the time, all right? And you'll be using multiplication there instead of division. Same goes with the work practice problems as well. Now, in history, before engines and motors were invented, people had to do things like lifting or pushing heavy loads by hand. Using an animal could help. What they really needed were some clever ways to either make work easier or faster. This is where simple machines came in. Ancient people invented simple machines that would help them overcome resistive forces and allow them to do the desired work against those forces. Now, a simple machine's device makes performing work easier by accomplishing one or more of the following functions: transferring a force from one place to another, changing direction of the force, increasing the magnitude of the force or the size of it, and increasing the distance or the speed of that force. Okay? Now, once again, remember work is force times distance. If you are doing the same amount of work, if you decrease the force, you increase the distance. Okay? If you decrease the distance, you increase the force. Now, this is a trade-off here. So if you make work easier by reducing force, your effort, or you can make work faster by reducing the distance, but you can't do both. It's one or the other here, ladies and gentlemen. Now, we're going to begin going over some simple machines: incline plane, wedge, and screw. In the up-and-coming presentation, it'll come out for the webinar on Wednesday, or on the next video will be on Thursday. Okay. Here is a practice video game. You can type this short URL link. The point of this is looking at how simple machines can be mixed together to make complex machines. In this case, Tom's Trap-O-Matic. Tom from Tom and Jerry. Tom is trying to catch Jerry. This is a little bit tricky and a little bit difficult, but it's fun and it pushes your understanding and learning. Okay, mechanical advantage. Mechanical advantage is a ratio of output force divided by input force. If the output force is bigger than the input force, a machine has a mechanical advantage greater than 1. If a machine increases an input force of 10 pounds to an output force of 100 pounds, the machine has a mechanical advantage of 10. In machines that increase distance instead of force, the mechanical advantage is the ratio of the output distance and the input distance. For example, this would be with pulleys. It is useful to think about a machine in terms of input force, the force you apply, and the output force which is applied to the task. When a machine takes a small input force and decreases the magnitude of the output force, a mechanical advantage has been produced. No machine can increase both the magnitude and the distance of a force at the same time. Remember that. Okay? Now, IMA, ideal mechanical advantage, and AMA is actual mechanical advantage. Now, you might be wondering, why are we talking about theoretical output force divided by 3 input force versus actual output force, actual input force? This is why, ladies and gentlemen. You cannot just put the basic weight or length, the force or pull that you're putting into it, that push or pull for a force, because there are other things such as friction and flexing of the material, gravity that can affect this output and input forces. So this is the reason you have theoretical and actual. Okay. Now, our first simple machine I'm looking at is an inclined plane, and it gets its IDMA from the length or effort distance divided by the height or resistance distance. All right? Here's a simple equation of that shows how you take the length and divide it by the height, and you get a mechanical advantage of 5 here. While the inclined plane produces a mechanical advantage, it does so by increasing the distance through which the force must move. Okay? Now, although it takes less force for car A to get to the top of the ramp, all the cars do the same amount of work. This is because our length here is the same. Okay? All right? Now, Here are some examples of inclined planes: a wheelchair ramp, a boat ramp, and hatchet. Now, there's other ones we don't think of all the time, like dump trucks, ladders, roller coasters. Our next simple machine is the wedge. Okay, it's getting its IMA from the length and the separation of the wedge surface, this thickness on the side. Okay. Now, the mechanical advantage of a wedge can be found by dividing the length of either slope by the thickness of the big end. Okay. As an example, assume that the length of the slope is 10 inches and the thickness is 4 inches. Your MA will turn out to be 10 over 4, or simplified to 2.5. As with the inclined plane, the MA gained by using a wedge requires a corresponding increase in distance. Okay. Some other examples of wedges are fork and knife, screwdriver, golf club, and other ones that we come in contact all the time with: nails, teeth. Nail goes through wood, teeth goes through food, a ship cuts through water. And our last one we're going to go over is a screw. Okay. Now, a screw has an MAA, and this involves 2 pi by the length over P. All right, and let's see what P is. This is the pitch. Now, the screw is an inclined plane wound around a central cylinder. And as you can see in the image here, if you took an inclined plane and you wound it up, you end up with a screw. All right, and it screws around us all the time, from threads to jar lids to drill bits. The mechanical advantage of a screw can be calculated by dividing the circumference by the pitch of the screw. Okay. And some examples: a swivel stool, bottle lids, corkscrew. And some other ones you might not think of: that screw that's in the tumbler of a door lock, light bulbs, and a C-clamp. Okay. Now, next time we'll be going over lever and the other simple machines, and looking at some ancient engineering tools that have been created throughout time in the ancient civilizations of our history. All right, thank you, and